Welcome, Laura. It's nice to see you again.
Thank you.
We're at Supercompute 2024. It's a lot going on, but it's a pleasure to be here with you. So can you tell us a little bit about what you do for NASA?
Sure. I am the high-performance computing lead for the NASA Center for Climate Simulation. It's one of the two supercomputing facilities within NASA. And we're located in Greenbelt, and we are, to be honest, the smaller of the two facilities. Earth Sciences is our main group, astrophysics, heliophysics, and planetary sciences. So we do all of those, all that work on our supercomputer.
Amazing. And so all that work on your supercomputer, can you tell us a little bit about what it is exactly that you're studying or really passionate about right now?
So within the Earth Sciences, the main goal is climate research. And that can mean some climate change work, but it also means things like the GMAO group, the Global Modeling and Assimilation Office, does a lot of aerosol work. So they run a climate model, but they're particularly interested in how aerosols transfer through the atmosphere. So air pollution or carbon or nitrates or sulfates. And they do beautiful visualizations, which you can see through the scientific visualization studio work that just shows off the tremendous work that they do for us.
Amazing. And so I'm fascinated by these aerosols. So you can see how they're penetrating all the way through to like the atmosphere?
Right. Since it's a three-dimensional model, you can see it move across, like you could see dust move from the Sahara Desert across the Atlantic and land in Florida. You can see it spin up in hurricanes, and you can see sea salt along the bottom. Usually gets picked up off the ocean around the poles. So they visualize this and they do great work with it. You also can see emissions from power plants, etc., that then get integrated into our atmosphere, or fires as well.
Wow. Okay. So you're doing all this work you mentioned on a supercomputer.
Yes.
Can you tell us a little bit about, is there a special name for the supercomputer?
Yes. So our Discover is the name for our supercomputer, and it was designed in about 2006. And the way it works actually is we are power constrained, so we only have so much power, and we get money every year. So we build out the supercomputer until we run out of power, and then when we get more money, the oldest part of the supercomputer has to be decommissioned, and then we bring in the new piece. So over all of those years, we have continued to add what we call scalable units and scalable compute units, and so we are now at we've got a little bit of 14, we've got 16, 17, 18 on the floor right now that our scientists can use, and it was initially Intel chips, and we have now moved to AMD. We also, all of Discover is CPUs with a small pocket of GPUs for testing and learning and new development. We also have a much larger GPU facility called Prism, which, again, a lot of development has gone there and a lot of really interesting science has come out of Prism as well.
Amazing. So what about the storage? Do you know much about the storage layer within the system?
We have storage for all of our systems. So we have the traditional HPC, which is Discover, and it has 60-ish petabytes of storage. We have centralized storage, which is intended for curated NASA data products. So these are things like MODIS data, Landsat data, Mira 2 data, things that are well understood as a climate, sorry, not climate, but well understood as a NASA data product. Then that data is also available through our on-premises cloud environment, which includes Prism. So all of that data can be accessed through all of those systems. We like to think, and we hope we're right, that it reduces the amount of duplication of the data on the systems, which allows for more room for new science to be done.
Yes, and more science as you're getting tons and tons of data coming in, right, from all these places to, look at climate change.
Yeah.
How are you guys able to, deal with that data once it's coming in? What is it are you looking at it on a daily basis? I heard, I was just talking to Bill and he said they archive everything. So are you doing the same thing?
We do not archive as much. We actually use Ames out at Bill's facility to do some archiving. But what we are trying to do is keep this data on spinning disk so that scientists can do science on it. And we're not funded as an archive. So that is really just a drag on our resources that prevents us from doing more supercomputing. But we do have somebody who is really good at his job who does data management plans. So we work with our users to get them to tell us what's their input data, their intermediate data, which will one day be deleted, and their final data products. How big is it? How fast does it grow? And that allows us to plan our storage requirements and get the right storage in place at the right time.
Okay. What if I told you mentioned spinning disks, and Bill said the same thing. Well, we just came up with a device called a solid state drive, which is 122 terabytes in this one little guy. Look how light it is.
That's pretty cool.
It's pretty light. Yes. Just to curiosity, like I know you're not a storage person, right? But with all those spinning disks being in that system,
Would we replace them? Yes, we would, if we could afford them. So the spinning discs do two things. One is, they're reliable and they're not terribly expensive. So reliable up to a point. So we're happy to have them, we're familiar with them, they work, et cetera, but they do take a lot of power. And as I said earlier, we're power constrained, so anything I can do to reduce our power footprint would be great. SSDs, a solid state, whatever it is, it's not like it's no power, but it's less power. So one of my goals has always been to find the right solutions that we can afford in order to actually move to more solid state. One of our challenges is that the data that is used for climate research is NetCDF data, which is already very much compressed. So a lot of the cost models for solid state are, hey, we'll compress your data even more and it'll work out from a cost perspective, except my data won't compress. So it makes it really, really hard, but we're still moving in that direction because of performance. And we absolutely have some that is critical to being allowed to run the models with the faster chips that we have now. Without it, we would be struggling. So, yes.
So let's take a step back and not talk about data, Shmita, right? But what about AI? Are you guys really doing, I mean, I've talked to a lot of folks here and everyone's doing some kind of AI, but so tell me a little bit.
So what are we doing? So as I said earlier, like when we brought Prism online 4 years ago, it was just people like, I don't know, I'm going to give it a try. And so it was just daytime access, and they were really just working on how this might work for their systems. And after time, they started to actually run things. So whether or not they're doing training model runs or doing some inference. So now our utilization is much higher than it was before. We are buying an expansion to Prism, which are actually going to be NVIDIA, the Grace Hopper nodes. We'll have about 60 of those. And we have two places where we're using the GPUs. One is in the machine learning, where we're working on some foundation models for earth science, but also taking that climate code and converting it to work on the GPUs. And that's a different group that is taking care of that. I do want to tell one kind of fun story, one of my favorite stories, about combining HPC with machine learning. This was probably 2 years ago. One of our users who came in and he said, I've got this test data from the Transiting Exoplanet Satellite Survey, and they were looking for binary stars. So what you do is you generate light curves to show how does the light change over time, and with most of these stars, it'll be a pattern. And if it's a binary star, you can take a look at that pattern and say, oh, that's a binary star. And so they used our supercomputer to calculate, I haven't had to look at the numbers in a bit, maybe 1 million light curves or more, many, many hours of supercompute time. Then they took all those light curves and then moved them over to Prism and did machine learning on them. And then they found outliers. They found a lot of binary stars. They found, they also found unusual systems, including some stars that are binaries with binaries, and one what they call sextuple system, which is 6 stars that are gravitationally bound. So there's 3 pairs of binary stars, and they all rotate around each other. And that was found only because we had a combination of HPC to generate the light curves and the machine learning to actually find the anomalies that allows them to key in on the ones that looked of particular interest.
Amazing. Yes. Is this a new recent discovery?
No, this is about 2 years old.
Okay.
Maybe 2.5.
Yeah. It's still pretty new though, in the grand scheme of things.
Yes, exactly.
Oh, very, very cool. Well, I have to ask you, because this cool image of the black hole here, you mentioned that this was also
done. Yeah, this was also done. The same group, actually. Yeah, same group. And while I do have a background in astronomy, this one is a little bit beyond. I'm not going to be able to explain it technically, but it was done on Discover. And if you watch the video, which is really important, you can actually feel like you're being pulled into the event horizon of a black hole, which you don't want to do yourself because you're not coming back out. It hit the social media and it just spread like wildfire because it is just a fascinating display. And all of the calculations were done on Discover.
Well, thank you so much for your hard work in your organization, everything you've done. It's amazing. And it's a pleasure to meet you, Laura.
It's great to
meet you
as well.
so much.
Thank you.